All right, so we're going to go ahead and start off with section E1.1, which is polynomials and factoring. So I'm going to do a brief review of pieces of the polynomials, okay? The degree of a polynomial is the degree of the term with the highest degree, okay? The degree of the term with the highest degree. Okay, so we look at all of our terms, and whatever the highest power of the variable is, that is the degree of the whole polynomial. Okay, then our leading coefficient is the coefficient from the term with the highest degree. Okay, or the coefficient on the highest degree term. Okay. And then descending order, we always want to write things, when we write polynomials, we always want the highest order term first down to the constant term. So what that means is the highest degree down to the lowest. Right in order. Highest degree to lowest. Okay. So looking at this, when we look at the highest degree term, or if we wanted to look at what we just learned, the degree of this polynomial, I look at the highest power of x in any given term. So that would be this one. So that means that this polynomial is a degree 12 polynomial. Okay, and I want to write it in descending order. So for this one, I would write 6x to the 12th, then my next lowest power or degree term would be x to the 10th, so I do plus 18, x to the 10th, minus x squared plus 3. Okay, so this is in descending order. This means that the degree of this polynomial, the highest order term I have is x to the 12th, so this would be a 12 degree polynomial, and then my leading coefficient is the number part of the highest degree term, or the coefficient on the highest degree, which in this case would be 6. Okay. All right, so I want to quickly review multiplying expressions, and then we're going to do a quick review of factoring. So when we multiply expressions, we multiply each factor by the other factor by multiplying each term of each factor by each term of each other factor. In other words, if I have something like x minus y quantity squared, I don't just do x squared minus y squared, because what this means is I'm doing the quantity x minus y and I'm squaring it, which means I'm multiplying it by itself. So from here we need to FOIL or distribute. So I'm going to take the x and I'm going to distribute it to each term. Okay, so x times x gives me x squared, x times negative y gives me negative xy, and now I need to distribute the second term to each term of the second. So negative y times x gives me negative xy, and negative y times negative y gives me positive y squared. And then the last thing I do is combine my like terms. Notice I do it in two separate lines so I can line up my common terms, my like terms. You don't have to do it that way, but you do have to combine like terms before you get your final answer. So this would give me x squared minus 2xy plus y squared. Okay. So quick little brush up on multiplying. Now I want to look at factoring. Factoring is the opposite of multiplying. When we factor, we're trying to break it into things being multiplied, okay, that equal the original polynomial. So first thing we look for is a greatest common factor. That is the largest number and or variables that we can take out of each term without being left with a fraction. Okay, so I'm going to put on here common numbers and variables. Okay, and we want the largest that we can take out of both. So looking at this, the common numbers, the common factor is 3, and that's the largest number we can take out, because if I take out more than a 3, the second term obviously can't handle it. So I can take out a 3, and I can also take out an x. I can only take out x to the first power because the second term only has x to the first power. Remember, when I take out a greatest common factor, it's like dividing it out. So 6x squared divided by 3x leaves me with 2x. 3x divided by 3x leaves me with 1. We always write our greatest common factor and then in parentheses what's left over after we take that out. Same thing on this one. I'm looking for greatest common factor. Notice not all three terms have a variable. If they don't all have a variable, then all we can look for is a number greatest common factor, which in this case, the number that divides all 24, negative 12, and 8 is the number 4. So if I take out a 4, I'll be left with 6x squared minus 2x plus 2. And that's as factored as I can get. Okay, I'm not going to go further. This one may factor, but for the sake, I'm just looking at greatest common factor. Okay, now I want to look at factor by grouping. Factor by grouping is used for 4 terms. When we do 4-term factoring, we always look for greatest common factor first, which means look at all 4 terms. Is there anything I can pull out? In this case, there's not. So I'm going to go straight into grouping, which means I pair off 2-term pairs, and I look for greatest common factor within them. So notice in the first 2, I can take out an x, which leaves me with y minus 7. And then if I want to be left with a y minus 7 over here, I'm looking for a common factor that will give me this leftover. So notice they're both divisible by 3. So if I take out a positive 3, I'm left with y minus 7 in my second grouping. Okay. Now they both have the quantity y minus 7. So if I take y minus 7 out of both of these terms, the first term I'd be left with only x. Second term I'd be left with positive 3. And now I have something that's completely factored. Okay. Same thing over here. Want to do the same idea. There's no greatest common factor for all 4 terms, so I'm going to go straight into grouping. In the first pairing, I can take out a 3x, which leaves me with 4y minus 1. In the second grouping, I can take out a positive 2, which leaves me with 4y minus 1. And then again, when they have the same leftovers, I can then take the leftovers out. So if I take out that 4y minus 1 quantity, it leaves me with 3x plus 2. All right, so let's scroll on down. The next thing I want to look at is sum product, which is also known as the AC method. Some of you may learn trial and error. That's fine with me as long as you can do it accurately. The way we teach it at Eastern is to use a sum product chart and replace the middle term. That's how I'm going to show it in this class. If you can do it another way accurately, that's fine with me. So when we use the sum product chart, what we're looking for is something that sums or combines to a certain number and multiplies to another. So I can replace this middle term with 2 terms so that we can do grouping. So my sum is always my middle coefficient, which here in this case is a 1. And my product is always my leading coefficient times my constant or my last coefficient. Okay, so in this case, my leading coefficient is a 6. My last coefficient is a negative 2, which means that my product is a negative 12. So I'm looking for something that I can multiply to get negative 12, that I can sum or combine to get a positive 1, which in this case would be 4 and 3. If I want to be left with a positive 1, that means my 4's got to be negative. Okay, still works. Negative 4 times positive 3 gives me the negative 12 of my product. Negative 4 plus 3 gives me the positive 1 I need for my sum. So what I'm going to do is I'm going to take these 2 numbers and replace this middle term. When you replace the middle term, make sure you keep the label the same. So here my middle term label was x. So I'm going to replace this plus x with minus 4x plus 3x minus 2. And then I'm going to go ahead and group, just like we did before. So here I can take out a 2x, which leaves me with 3x minus 2. Now if I want to be left with 3x minus 2 here, and I already have it, the only thing I can take out without changing the value is a positive 1. If I divide anything by 1, it stays the same. So now I can take out their leftovers, which is 3x minus 2, and I'll be left with 2x plus 1. Okay. And now I'm fully factored. Let's look at a few more, and then we'll look at a couple other types of factoring. So on this one, same thing. I'm going to use sum product. My sum is my middle coefficient, which is a 3. My product is my first coefficient, which is a 1, times my last coefficient, which is a negative 20, which gives me a product of negative 20. So to multiply to get negative 20, I can use 20 and 1, I can use 2 and 10, or I can use 4 and 5. Notice none of these are going to give me a difference or a combination of 3, right? 20 and 1, 2 and 10, 4 and 5, no matter how I subtract them, is not going to give me a 3. So if I can't find one that works, then that means that this is not factorable. Not factorable. Okay. All right, let's look at another one. 7x squared plus 23m minus 20. There's no common factor between all three terms, so I go straight into my sum product table. My sum is my middle number, which here is 23, and my product is my first number times my last. So if I do 7 times negative 20, that gives me negative 140. So I need something that combines to 23 that multiplies to negative 140. So when I try to find a combination, I look at what can I multiply to get 140. Well, the way we got 140 is we did 7 times 20. So if I look at that, 7 and 20, that doesn't work, right? That's going to give me, what, negative 13? That doesn't work. So let's find something else. It ends in a 0, so I know 10 goes into it. So 10 and 14 gives me 140, but 10 and 14, when I combine them, is either going to give me 4 or 24. So that doesn't work. So let's go ahead and something else that goes into it. It ends in 0, so I know 5 goes into it. 5 goes into 140 28 times. And notice that will give me what I need. I will use a positive 28 and a minus 5. So I'm going to replace my middle term with the two numbers I just found. So I have 7m squared. I'm going to do plus 28m minus 5m minus 20. And then go ahead and group just like we did before. Out of the first two, I can take out a 7m, which leaves me with m plus 4. Out of the second pairing, if I want to be left with m plus 4, I need to take out a 5, but if I want the signs to change from negative to positive, I want to divide off that negative as well. So instead of taking out a positive 5, I'm going to take out a negative 5. So that leaves me with m plus 4 when I take out my leftovers. From the first term, I'm left with 7m. From the second term, I'm left with negative 5. Okay. This next one, same idea. The only difference here is we have a greatest common factor. We're going to take the greatest common factor off first, which is negative 5. When I take off a negative 5, I'm left with x squared plus 5x plus 4. Okay, and then with what's left over in here, I'm going to do sum product. I need something that combines to 5 that multiplies to 4. The only way to get 4 is 2 and 2 or 4 and 1. Obviously, we're going to do 4 and 1. Now, the good thing about doing sum product, anytime you have a leading coefficient of 1, whatever the numbers are in your chart, those are the numbers that are going to be in your factors. Okay, I went over this a little bit in 118. So I could replace the middle term and group, or I can use my shortcut. Okay, I'm just going to say shortcut because my leading coefficient is 1. Okay, so I get negative 5, which is my greatest common factor, and then I know the values from my chart are the values in my factors. So this factors into x plus 4 times x plus 1. Okay. All right, I want to show you the same type of problems, but a little bit more difficult that we have to use substitution on. And then I want to go over sum and difference of cubes, and then I'll have y'all work some. Okay. All right. So the first one, sometimes we have to use substitution because we notice that it looks kind of like a 3-term polynomial that we could use sum product on, but the exponents are a little bit larger than what we're used to working with. So I can do one of two things. I can say let y equal x squared. If I let y equal x squared, then I can replace this one with just a y, and I can replace this one with, well, if y is equal to x squared, then what power of y would give me x to the 4th? What am I doing? To go from x squared to x to the 4th, I'm squaring it, right? So if I say let y be x squared, then to square that to get x to the fourth, this one would be y squared. So I could rewrite this as y squared minus 2y plus 1. And now this is something that's easy to factor. If I factor this one, I need a sum of negative 2 and a product of 1, which I could use negative 1 times negative 1, because negative 1 times negative 1 gives me positive 1. Negative 1 minus 1 gives me negative 2. So I know right away this factors into y minus 1 and y minus 1, but remember we did a substitution. So then we have to go ahead and plug back in. Okay, we know that our y, excuse me, is x squared. So once I have my answer, I need to go ahead and put back in what y was. So I'm going to say plug back in. So this really factored into x squared minus 1 and x squared minus 1. Right? Now, this is actually a difference of squares, which we're fixing to go over in just a second. Most of y'all have seen a difference of squares. Difference of squares factors into the first base plus or minus the second base. So both of these are a difference of squares. So this would end up being, this first one becomes x plus 1 times x minus 1. The next one becomes x plus 1 times x minus 1. And then I can go ahead and simplify this by writing those quantities. Since I have repeats, I could write them squared. So I could leave it like this, or I could say this is the same as x plus 1 quantity squared times x minus 1 quantity squared. Okay. And we'll do some examples of that in just a minute if you're not used to seeing that. Okay. This one again is one that we can do by substitution, so I'm going to go ahead and again say let y equal x squared. So that way I can replace this with just a first degree y, and I can replace this one with y squared. So that gives me y squared minus 2, oops, not 2x, 2y minus 15. And then I can do sum product. I need a sum of negative 2 and a product of negative 15, which to get a negative 2 I would use negative 5 and positive 3. Because my leading coefficient's a 1, I can just use the shortcut. I know these numbers in my chart are going to be my factors. So this factors into y minus 5 times y plus 3. And then the last thing I do is plug back in because I use substitution. Plug back in. So y we know is x squared. So I need to put that back in for each of my y's. So this gives me x squared minus 5 and x squared plus 3. Okay. Now, neither of these, this is a sum of squares. We can't go further. I'll show you that in a minute. A difference of squares, each term has to be a difference, meaning subtracted. And it has to be a, each term within the difference of squares needs to be a perfect square. So here, even though I have an x squared, 5 is not a perfect square. I'm going to say not a square. Okay, so if it's not a square, I can't go any further, and I'm just going to leave it like that. Okay, so I can't go any further because 5 is not a square. All right, so now I want to go ahead and go over difference of squares. Difference of squares, we always look for greatest common factor first, and then when we're working out a difference of squares, I'm going to go ahead and put it over here. Anytime we have x squared minus y squared, this always factors into x plus y times x minus y. That's our formula. Okay, so this is one you need to be familiar with. So on this one, all I have to figure out is what do I have to square to get 16x squared, and what do I have to square to get 9? Okay, in order to get 16x squared, I would have to square 4x. In order to get 9, I would have to square 3. Then I just plug it into my formula, so I do my first base plus or minus my second. So I'm going to do 4x plus 3 times 4x minus 3, and I'm completely factored. Okay. On the next one, again, I look for a greatest common factor. Always, 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 that's my first step. So if I take out a 6, I'm left with x squared minus 6. Okay. And then from here, I would like to do difference of squares, but unfortunately, 6 is not a square. So if 6 is not a square, I'm not going to break this into x minus the square root of 6 and x plus the square root of 6. That's just a little redundant and ridiculous. So I'm going to go ahead and just leave it just like this. So on this one, we were only able to pull out a greatest common factor. Okay. All right. Let me look at one more difference of squares, and then I'll show you sum and difference of cubes, and then I'll have y'all try some. Okay. All right, last one, easy enough. What's my base here that's being squared? An x. What's my base here that's being squared? Would have to be a 5. Plug it into my formula. First base plus my second base. First base minus my second base. And this is fully factored. Okay. Now, sum and difference of cubes is a little bit different. There's a formula and you just have to memorize it. Okay, I won't give it to you on a test. I won't give it to you on the final. It's just something you need to know. So I'm going to go ahead and write down what our two formulas are. They're using a's and b's here. If I have a cubed minus b cubed, notice my base here would be a, my base here would be b. My formula is I do my first base minus my second base times my first base squared plus I multiply my two bases together, a, b, plus my second base squared. Okay. So if this starts out as a difference, your first little quantity is a subtraction, and then your next sign is a plus, and then the last one's always positive. Okay. Now if I start out with a sum of squares, again my base here is a, my base here is b, I write my first quantity with the same sign that my original was, so since this is a sum of cubes, I'm going to do a plus b. And then again, I square my first one, a squared, but this time I switch to minus, multiply them together, ab plus b squared. So notice these two formulas are almost identical. The only difference is the first two signs. In the first quantity, if you start out with a subtraction, you have a subtraction. If you start out with a sum, you have a sum. And then whatever the first sign is, the next sign is opposite that. Okay? The third sign is always positive. So let's go ahead and look at an example. So my example here is t cubed minus 8. My base that's being squared here is a t. My base that's being, no, sorry, not squared, cubed. My base that's being cubed to get t cubed is t. My base that's being cubed to get 8 would be 2. Now this is a difference, so I'm using this formula. This formula says that I do my first base minus my second, so t minus 2, times my first base squared, so t squared, plus I multiply my two bases together, so 2 times t or t times 2 gives me 2t, plus my second base squared, so 2 squared, which would give me 4. Now, the good thing about sum and difference of cubes is once you've plugged everything into this formula, this second factor is always prime. Okay? So you never have to check to see if it will factor further if you're doing sum and difference of cubes. That second factor is always prime. It will never be factorable. Okay? All right. So let's look at one more and then I'll have y'all work on sum. This one is the same thing. It's a sum. To do a sum, I do it the same way. Look for greatest common factor, which here I don't have one. And then I figure out what are my bases that are being squared. My base here, what do I have to cube to get 27? 3. What do I have to cube to get x cubed? X. Here, what do I have to cube to get y to the 6th? So I'm looking at, what cubed gives me y to the 6th? So 3 times what number gives me the 6th? It would have to be a y squared. So my base here is y squared. So I'm going to go ahead and plug it into the formula above. I do my first base plus my second. So 3x plus y squared. Then I do my first base squared. So I'm going to do 3x squared minus my two bases multiplied together. So I'm doing 3x times y squared plus my last base squared. So y squared squared. I went ahead and wrote this one out just so that we don't make mistakes by assuming we know what we're doing. So I have 3x plus y squared. When I simplify, 3x squared gives me 9x squared. When I multiply 3x and y squared, I get negative 3xy squared. And then y squared squared is y to the 4th. Okay. So I'm going to go ahead and circle that. Now, on the next page, well, at the bottom of this page and on the next page, there's several for y'all to try. Okay, I think there is a total of 6. Yes, there's 6 for y'all to try. I'll give you a minute to do them, and then I'll show the answers up here if you have any questions, okay? All right, so I'm going to go ahead and talk about this one. The first one, all we have to do is take out a greatest common factor of 2. Then after that, we can use sum product. When we do sum product, our leading coefficient's 1. So once we find the pair in our chart, which should be -4 and 2, we know those are our factors. Okay. On the second one, we can take out a greatest common factor first, which is 3x squared. Once we take that out, we notice our polynomial is not in descending order, which is not good for having to factor. So we reorder it. Once we reorder it, we need a sum of 12 and, I'm sorry, a product of 12 and a sum of -4, which with the factors we have is not possible. So we don't say it's not factorable. It's only not factorable if we can't even take out a greatest common factor. But since we were able to take out a greatest common factor, it is factorable. We just can't factor it any further. So that's our answer. On the third one, we're looking at a difference of cubes. So we determine what our bases are that are being cubed, which is 5y and 1. We plug it into the formula and simplify. Okay. On number 4, same thing, we have a difference of squares. Difference of squares, we identify our bases, which is x and 7, and then just plug it in. We get x plus 7, x minus 7. And then number 5, I use substitution. I let y equal x cubed so that I would have a polynomial that has a y squared and a y, which is something I know how to factor. Okay. We use sum product using the shortcut because our leading coefficient is a 1. We get the factors y minus 5 and y plus 4, and then we plug back in. Now what we're left with looks like it could be a sum and difference of cubes, but since 5 and 4 are not perfect cubes, we don't go any further. We just leave it right there. Okay. On 6, we don't have a greatest common factor, so we go straight into sum product. We need something that combines to 13 and multiplies to -14, which is 14 and -1. We replace the middle term and group, which should give us x plus 7 and 2x minus 1. Okay, so that is the end of E1.1, so you can now complete that homework assignment in my math lab. Let me know if you have any questions.